This is your lecture on circular motion. You're going to find the information on Chapter 6.2, Circular Motion, and Chapter 6.3, Centripetal Force, Gravitation, and Satellites. And you guys just went over the universal law of gravitation and just went over the orbits lab, so I'd encourage you to think about those labs as we talk about this lecture. Okay, so motion in circles. When we say an object rotates about its axis, when the axis is part of the moving object. We talk about something revolving on a merry-go-round because the person is external to the merry-go-round's axis. So planets and stars revolve around each other while bicycle hubs and motorcycle hubs rotate. Okay, angular speed is the rate at which an object rotates or revolves. So that's basically how fast the bicycle wheel is spinning. And there are two ways to measure angular speed: the number of turns per unit of time and the change in angle per unit of time. So the change of angle per unit of time is something called degrees per second or radians per second. And the number of turns per unit of time is also rotations per minute. And that would go back to your understanding of waves, how many cycles per second it was passing through. Angular speed. There are 360 degrees in a full rotation, so one rotation per minute is the same angular speed as 360 degrees per minute. So that can be considered pretty quickly. So the number of degrees over the amount of time is equal to the angular speed, very similar to the amount of distance divided by time. So angular speed, distance divided by time, rotations are degrees. Linear speed, the way that you would calculate that is you would take 2 pi r, and that is the circumference of the circle, or the total distance traveled if you took this line and stretched it out into took this curve and stretched it out into a flat line. So that's how you would calculate linear speed. The pi is 3.14 and the r is the radius. So that would be the length of the spoke in the wheel. And that's how you would get the linear speed. There's some practice for calculating linear speed. We're not going to do that. I did want to point out, though, that RPM stands for rotations per minute. And so you'll see some motorcycles going on a 500 RPM or 600 RPM or 600 horsepower. That's rotations per minute. So that talks about how fast it rotates. You also see some kind of saws, circular saws talk about how many RPM, or drills talk about how many RPM. So the relationship between linear speed and angular speed. Each point on a rotating object has the same angular speed. So Dwayne and Ryan are moving at the same angular speed, but they are traveling at different linear speeds. Imagine a bicycle wheel and a hub where there's a little tab or a piece of tape towards the beginning of the hub, and then there's a bicycle tape at the very end of the hub, right near where the rim is. And they both have the same angular speed. They're both doing the same degree rotations per minute, but the linear speeds are different. The one that's closer to the hub is going to cover less distance and the same amount of time as the one that is further away, which has to cover more distance in the same amount of time. It's similar to marching band when they're doing a turn or a curve. The people on the inside where the curve starts or rotates, they walk really slowly so that the people who are at the far extreme of the curve walk much quicker to cover the same amount of distance. So angular speed throughout the whole system is the same, but linear speed is different depending on how far away you are from the middle, or depending on how far the radius is. So circumference is just a picture here. That's the distance around the circle. And the distance traveled during one revolution is equal to the circumference of the circle. Linear speed is, we're going to talk about the relationship between linear speed and angular speed. Linear speed of a point at the edge of a turning circle is the circumference divided by the time it takes to complete one full turn. And the linear speed of a point on a wheel depends on the radius r, which is the distance from the center of the rotation. So basically how long the spokes are, how far away the merry-go-round is from the center, how big the Ferris wheel support structures are from the center of rotation. And you can calculate linear speed. We'll practice that later. So we're going to talk about linear motion, rotational motion, and rolling motion, okay? Because they are three separate things. Linear motion is just going straight. So the distance that your speedometer or odometer reads as you're riding your bicycle, that's the linear motion, right? But the rotational motion is greater than that because it takes the wheel a full cycle. So what linear motion really is linear rolling motion. Linear motion plus rotational motion is equal to rolling motion. There's a special kind of friction that deals with that. And then linear distance is equal to the circumference. So the distance the bicycle moves depends on the wheel size and the angular speed. When the wheel makes one full rotation, the bicycle wheel goes forward one circumference of the wheel. And we're actually going to move to 6.3, which is centripetal force, gravitation, and satellites. And there's going to be a little bit of discontinuity of the lecture because I got to pause it to get up the new slides. Okay, so we're back. We are going to be on chapter 6.3, which is centripetal force, gravitation, and satellites. And we've talked about linear motion, angular motion, and we talked about the relationship between them. Now we're going to talk about force, or specifically centripetal force. Any forces that causes an object to move in a circle is called centripetal force. A centripetal force is always perpendicular to an object's motion towards the center of the circle. So an easy way of thinking about it is if you've, a classic example would be a sling. So biblical times, David versus Goliath, David had a weapon called a sling. It basically was a long string with a pad in the middle, and you would put a stone in the pad, and you would hold the two strings at the end in your hand, and you would swing the strings around your head, kind of like this guy is doing. And then when you let go of one of the strings, the stone would move tangent to the path and move really, really fast and hit the object that you were trying to kill, whether it was a lion or a person or whatever. So that's an example of centripetal force. The string had some tension to keep the stone or whatever's at the end of it moving around in a circle. And then on the car example, it's kind of difficult to understand how there's centripetal force in a car, but it's really the force of friction on the road. That's why the angle of the ramp is really important when they're doing NASCAR races or other kinds of races, motorcycle races, because you got to have the right angle to provide enough frictional force for the car to go down the road. So centripetal force and direction. Whether a force makes an object accelerate by changing its speed or by changing its direction or both depends on the direction of the force. So we've talked about acceleration needing to be a speed up, and you can see an example of that where the force and the velocity are building, so the acceleration is in the same direction as the velocity, and that's speeding up. You've got slowing down, where the force and the acceleration are going opposite the direction of the velocity, so the velocity is losing speed. And then you've got turning, where the force is perpendicular to the direction of the velocity, and that makes a curve happen. Okay? So let's speed up, slow down, or change in direction, and centripetal force is based off of that curve or that turning. Yeah, vision up. So centripetal force, we've got a man who's tying a ball to the end of a string and twirling it in a circle over your head. The string exerts a centripetal force on the ball to move it in a circle. The direction of the force changes constantly as the object moves it around you. So in no 2 seconds is it going to be doing the same direction. It's going to be doing similar directions. But the important idea is that the force is pointing always center to the object of rotation. So if you tie a ball on a string and keep the initial velocity to the left, so here's our left, it will keep moving straight to left. An object in motion stays in motion. But that's where the force comes into play, is there's a force pushing it inward, which makes it change its velocity in the next rotation or next picture. So you can see kind of the curve that's happening. The force is always pointing inward and making it go on that curve, while the velocity is trying to go tangent to where that circle is. Or tangent is 90 degrees from where the force was. So the centripetal force is now pulling to the right, and an object in motion wants to stay in motion. So B wants to continue going down this way, but the force keeps pulling it in towards the center, so it has to change its path. So the velocity is always perpendicular to the string, and therefore to the centripetal force. And you end up getting this circular motion because it's going tangent to the circle. So Newton's second law, an object moving in a circle at a constant speed accelerates because its direction changes. And that's how you get the acceleration, and that's how you get the force. So how quickly an object changes direction depends on its speed and the radius of the circle. The centripetal acceleration increases with the speed. So the faster you go, the more acceleration, and then decreases as the radius gets larger. So the bigger the circle, the slower the acceleration. That makes sense. So think about the Earth moving around the sun. It's a much slower acceleration because the circle is much larger, and that's why it takes 364 days for our Earth to go around the sun, whereas Mercury is only, I think, an 84-day cycle because there's so much more force, there's more acceleration, it goes faster. So centripetal acceleration is the rate at which an object's velocity changes as a result of the force, and centripetal acceleration is direction and velocity changes. And the reason why velocity changes is because the direction changes. You can see the change in the velocity arrows. That's equal to the acceleration, and the direction can change. So Newton's second law relates force, mass, and acceleration. The strength of the centripetal force needed to move an object in a circle depends on its mass, speed, and the radius of the circle. So you can see you've got a smaller circle where you've got a radius of 1 meter. The object is going 1 meter per second speed-wise, and there is 1 Newton of force. So you have a greater force for a smaller circle. Here, the radius is twice that. The linear speed is still 1 meters per second, but as a result of increasing the radius, the acceleration is actually smaller. Think about it. When you make a turn, when you're turning a sharp curve, you feel the acceleration. You slide to the other side of the seat if you're not buckled up. But if you make an easy turn where you're going a long radius, you don't feel that force as much, and the friction is enough to keep you in your seat. Okay? So think about the radius of the turns when you're thinking about force. So sharp turns, small radius, larger force. Slow turns, longer radius, smaller force. Okay, so this is a good place to pause for lecture, and we will have another video at another point in time to get you through the rest of the slides. So we're going to be stopping at slide 12, and we've got 25 to go.